So we had dilute today as an adjective, a dilute solution, modifying, telling me what type of solution I have, a modifier. Okay, but what does dilute mean as a verb? If I gave you a solution and I said, I want you to dilute this, what would you do? What would you do to make it a more dilute solution? You'd add more solvent. Right? You add solvent. Okay. So, let's stop and think about what doesn't change when I add water to a solution. What doesn't change? How much stuff I have in the solution, right? The solute doesn't change when I add water. So that means that the number of moles of solute doesn't change. The grams doesn't change. The moles don't change. My Kool-Aid tastes bland, though. Yeah. So I'm going to write this as an equation. I'm going to write this sentence right here as an equation. It's complicated. The moles before equal the moles after. And how can I figure out moles in a solution? Well, if I want moles, well, my only definition I have that has moles in it is molarity, right? And molarity is moles over liters. So if I want moles, I'm going to have to multiply both sides by liters, right? So that means I get to change this equation to this. M1V1 equals M2V2. Because M1V1 would be the moles before, right, Christian? M2V2 would be the moles after, and they have to equal each other. What kind of relationship is this? Well, because if I have more volume, I'll have less molarity, right? This looks just like Boyle's law, except it's not for gases. Okay. M is concentration, V is volume. As you read through homework and you read through the book, you're going to find that they refer to something called a stock solution. And they're using the word stock like Amazon uses the word stock. Okay? Stock means it's sitting on the shelf ready to be used. It's just pre-made to a known molarity. When I order hydrochloric acid, I have my choice about what concentration I order. I can order 0.1, 0.2, 0.5, 1, 3, 4, and 12 molar hydrochloric acid. I always order 12 molar because I can make all the other ones from the 12 molar. If I buy the 1 molar, I can make the less than 1 molar, but I can't make the more than 1 molar. So I buy the most concentrated stuff and dilute it down. Yeah. So when they say stock solution, all they're saying is it's sitting on the shelf ready to use. Somebody's already pre-made it to a known concentration. So there's nothing different about that solution other than it's sitting on a specific shelf. It's what you have available to you. Okay, so 2 liters of a 0.88 molar solution are diluted to 3.8 liters. What is the new molality? One volume, one molarity, second volume, they ask me for the second molarity. Anybody know an equation with those pieces in it? That's M1V1 equals M2V2, and I want M2. So I need to divide both sides by V2. So my M2 is going to equal M1, 0.88 molar, times V1, 2.0 liters, divided by V2, 3.8 liters, and 0.88 times 2 divided by 3.8 is 0.46, and the units are molar. Now we can check, does this answer make sense? The volume went up, so the concentration should go down. Fact is, the volume almost doubled, so the concentration got cut almost in half. See how those numbers work out there? So it's the same type of thing. Now let's kick it up a notch. You have 115 milliliters of 6 molar HCl. What volume of 1.3 molar HCl can you make? They give me one volume, one molarity, second molarity, and they ask me for the second volume. So M1V1 equals M2V2 again, except this time we want V2, so I divide both sides by M2. Will not let me write an M down there. I write it? Oh, let's let that one stay. I don't know why. So V2 is going to equal, I know I want M1 to be 6.0 molar, but the question is, can I do this in milliliters? Let's find out, because I'll just do it twice. Once in milliliters, 150 milliliters, and once in liters, which is 0.15 liters. Both those I have to divide by 1.3 molar. So in the first instance, 6 times 15 divided by 150 divided by 1.3, and I get 690 milliliters. If I do that numbers with the bottom one, I get, meters cancel off, and I get 0.69 liters. Did I have to change? No, I didn't have to change, because 0.69 liters is 690 milliliters. Right? So this will work in milliliters. Right? It'll work in milliliters. Okay. I run into this all the time. I have to make the solutions you want, and I only buy 12 molar hydrochloric acid, so I always have to dilute it down. I always have to ask myself this kind of question. How much do I need? Like in tomorrow's lab, I know I need 2 liters of solution to make it through the day. Okay, so how am I going to make that? So if I have 450 milliliters of a 0.15 molar NaOH, and all I have is a 2 molar stock solution, how do you make the required solution? Well, I got 2 molarities and 1 volume, so I'll be able to find the second volume. Everybody okay with that? So that V2 is going to be M1 V1 over M2, which is 0.15 molar times 450 milliliters divided by 2.0 molar. 0.15 times 450 divided by 2, and I get 34 milliliters. And you circle that answer, and Mr. Green marks it wrong. How do you make the required solution? 34 milliliters. See why that's not the answer? It's part of the answer, but it's not the answer. Okay, that's 34 milliliters, so here's how you would make the solution. You would take 34 milliliters of 2 molar and add water until you reach the 450 milliliter mark. Period. That's what you do. And you might say, well, you add 430 milliliters of water. Volumes are not additive. You say, oh, of course they're additive. No, they're not. And so, we're so used to things being added up, but it doesn't work quite as well as you think. So here I'm going to take 50 milliliters of water. Right at 50. And 50 liters of methanol. I can't pour it out of here very well, so I'm going to pour it into a beaker first. Do, 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 do. A little bit more. Okay. So, I have 50 milliliters of water. Is that 50 milliliters? Is the bottom of that curve right on 50? Yeah, is that 50 milliliters of this? Got 50 and 50. So, of course, 50 and 50 makes 97. It's only 97. It's not 100. Volumes don't add. That's why you have to word it that way. That's why you can't say add 430 milliliters. Or, does that make sense? You can't say add 416 milliliters. Because volumes don't add the way you think they're going to. Notice we have never said volume is conserved. We've always said mass is conserved. Particles are conserved. Volume's not conserved. It can change. So that's why you got to write it that way. I got to end up at 450. Make sense? Okay. So, this is the kind of thing I have to do all the time for your labs. You needed 3 molar hydrochloric acid. How did I make it? So what'd you get? M1 V1 over M2. It's going to equal V2. So that was 3.00 molar times 5.00 liters divided by 12.6 molar. So 15 divided by 12.6 is 1.19 liters. That's as hard as it gets. Okay. Okay, but we got to tie this into the moles of the compound is not going to be the same as the moles of the ions. Okay, so last time we looked at this, we saw what happened when it got to equilibrium. Let's see what Le Chatelie says about it. Okay. So I'm going to do the same thing. We got to pick what percentage of A is going to turn into B, and I want the numbers to be easy for me. So let's say 50% of A turns into B on every collision, and 20% of B turns into A. So when you first start off, after 1 unit of time, you'll have used up 50, and you will have made 20, or you'll have made 50. Okay. Right? Now 50% of those are going to change, so that'll be 25. And 20% of those are going to change, so that's going to be 10. You'll notice the slopes of the lines over here, that both slopes changed because the forward reaction is slowing down and the reverse reaction is speeding up. So this thing rounds, I think half of 35 is 18 according to this, and 20% of 65 would be 13. Okay, see our slopes changed again. Okay, now half of those, 15, are going to change. And 20% of 70 is 14. And that's 14. Oops, still 15. And that's still 14. That's still 15. Oop, nope, that's 14. And that's still 14. So now we're at equilibrium. 14 are going to change every time. So okay, so right now I'm at equilibrium. So let's say I add 50 more of A. I'll then have 78. And don't do any of those. Oops. So I've got 78. I've added some more of those. And 72 of those. Oh, that's too many. So maybe let's try this as, instead of make it 68. That's too many. Add 30 more, 58. Okay. So I've messed up the equilibrium. But what's it going to do? Well, it's going to continue on. So we're still at the 50%, so half of 58 is 29. And 20% of 72 is still 14. And half of 43 is 22. And half and 20% of that of 87 is 17. Half of that is 19. That's 18. 19. Is it 19? Okay. So you can see that I've reached a new equilibrium. And at the new equilibrium, there's more of B than there was in the original equilibrium. So even though I added A, it took that extra A and turned it into more B. So we would say that adding reactant, so I added A, makes more product. So I tried to add reactant, it tried to make product. It undoes what you did to it. So let's go back to there. So this is where we're at. We added reactants there. We increased their concentration. So what happens is the forward reaction speeds up, so more product will form. And since we've got to define reactants turning into products, if I just draw an arrow, draw my arrows, reactants turning products. Chemists say equilibrium shifts to the right because if it makes more products, that means on the right-hand side is products. Okay. I could also add products or increase their concentration. So that would be if I added B instead of A. If I added B instead of A. Well, that would affect the reverse reaction. So we were at equilibrium, the forward and the reverse were going the same speed. Now the reverse is going to win for a while. If the reverse wins, the reactant gets made. We say equilibrium shifts to left because reactants are on the left. We can't change where reactants and products are, so we say left and right. So if the reverse reaction speeds up, it wins for a while, you make more reactant. I could also remove products, get them to leave somehow decrease their concentration, and then the reverse reaction will slow down. Well, I had two reactions that were going the same rate, forward and reverse, and suddenly the reverse reaction is going slower. That means the forward one, which was still going the same speed, is going to win for a while. If the forward one wins, you're going to make more product. Make more product, we say equilibrium shifts to the right because products are on the right. So shifts to the right means makes more product. I could also remove the reactants because reactants doesn't mean what you pour in anymore. Reactants means the stuff on the left-hand side of the equation. If I remove the reactants, the forward reaction will slow down. So before they were going equal, and now the forward reaction slows down, which means the reverse reaction wins, which means more reactant will form. So equilibrium shifts to the left because reactants are on the left. So the idea here is that it undoes what you did to it. If you add products, it's going to use those products to make reactants. If you add reactants, it's going to use those reactants to make products. If you try to take out a product, it will make more of it. If you try to take out a reactant, it will make more of it. It will undo whatever you did to it till it gets back to equilibrium. So that's how concentration affects equilibrium. Chemists use this to control how much you get from a reaction. So what they like is something that makes two products. If you got product 1 and product 2, and the stuff you really want is product 1. But if you can find a way to remove product 2, as fast as you remove product 2, it's going to make more product and you'll get more and more product 1. So by taking out product 2, you can make more product 1. Or you can make sure your reactants have really high concentrations so that forward reaction wins. And you just keep that concentration of reactants high. So as you start using up reactants, you add more. So it just keeps that forward reaction going fast because there's lots of pieces to hit each other. My arrows got messed up. So there's an equilibrium. What's going to happen if Fe3 plus is added? Well, Fe3 plus is here. It's on the product side. So if I increase its concentration, this reaction is going to win, and equilibrium is going to shift, well, that arrow pointed to the left. I'm going to make more of my reactant. So if I add Fe3 plus, I'll make that ion. Okay. Here's my double-headed arrow. What's going to happen if I take SCN out? So if I try to remove SCN, it's going to undo that and make more. And the way it makes more is we say equilibrium shifts to the right. So use up the FeSCN to turn it into SEN. And the second thing we change is temperature. And reactions either release or require heat. If you're doing the extra credit, you'll see that those are called endo and exothermic. Exo means is like exit or exoskeleton, out. Therm for heat. So the heat comes out. So these are things that give off heat. Remember exoskeletons? Bugs have exoskeletons. We have endoskeletons. Endo means in or inside, so thermic, heat, heat in. These are ones you have to put heat into. Okay. So if you have a reversible reaction, one direction is going to be endothermic, the other direction is going to be exothermic. If it uses heat going this way, it'll release heat going that way. Fact is, we can put the heat right in the equation. Okay. And if I try to put in heat, Le Chatelie says it's going to undo what I did. It's going to use that heat to run a reaction. If I try to take out heat, it's going to make more heat. And along the way, it's going to make more of the reactants of the product. So if you raise the temperature, the reaction proceeds in the endothermic direction. If you lower the temperature, it goes in the exothermic direction. You try to raise the temperature, put heat in. It uses that heat to do the reaction. If you try to lower the temperature, it lets heat out to try to undo you lowering the temperature. So you try to raise the temperature, it says, no, we're not going to use that energy to make the molecules faster. We use that energy to make new chemicals. You try to take the energy out, it says, no, we'll make more energy by changing our chemicals. So if I have heat here, if it's at high temperature, the heat's a reactant, it's going to go that way. If it's at low temperature, it's going to try to undo that, and it's going to go to the left. So if it's going to go either towards the heat or away from the heat can be on either side of the equation. For example, if you want to melt water, here's the equation. We know that melting water is reversible. We can freeze water too. Okay. And if I take solid water, ice, and add heat, I make water. In order to make liquid water into solid water, I've got to take the heat out. That's why the back of my freezer gets heavy. So if the temperature is high, at high temperature, it's going to try to use that heat. You're going to try to put in heat, and it's going to use that heat and make liquid water. So at high temperature, water melts. At low temperature, if you try to lower the temperature, it's going to respond by trying to raise the temperature. It's going to make heat. Try to raise that temperature back up, undo what you did, and along with the heat, it's going to make solid water. So if you lower the temperature, water freezes. So, pretty easy example of how temperature affects an equilibrium. Oops, my double-headed arrow. Okay, predict the following when temperatures decreased. Okay, so that negative sign on heat means that the reactants lost heat, so heat is over here. Exothermic reactions have negative values. Okay, so if the temperature's decreased, it's going to try to make more heat. And the way it makes more heat is by using up the reactants, and turning them into products, so it shifts to the right. The third change we can make is a change in pressure. And here, Le Chatelie says it tries to undo what you did. So if you try to squeeze it and make the pressure higher, it's going to try to lower the pressure, and the way it can lower the pressure is by having fewer moles of gas. So the things that are gases will stop being gases. So at high pressure, hydrogen and oxygen make water. And the reason why it happens at high pressure is because this side has 3 moles of gas, and this side only has 2 moles of gas. So if I increase the pressure, it goes to the side with the most gas. And if I lower the pressure, it goes to the side with the least gas. So this side has 2 moles of gas, this side has 3. So at low pressure, you try to lower the pressure, it makes more gas molecules, so there's more collisions, and the pressure goes back up. So it tries to undo whatever you did to it. So low pressure to the side with the most gases, high pressure to the side with the least gases. So if I double the pressure, that means the pressure is going up. How could this system fight the pressure going up? Well, this side has got 3 moles of gas, that side has got 2 moles of gas. So if the pressure is doubled, it's going to try to lower the pressure by making less gas, which is the 2. So we're going to say equilibrium shifts to the left because that 2 is on the left. Okay. Here's another equilibrium. Carbon monoxide and nitrogen dioxide make carbon dioxide and nitrogen monoxide, which would result in the formation of more products. So I want more carbon dioxide, more NO. If I increase the pressure, what's going to happen? Well, this equation is balanced, so there's 2 moles of gas here and 2 moles of gas there. Which side has less gas? Neither side. So this means that there's not a side with least gas, there's no effect on equilibrium position. Removing CO from the reaction. If I remove CO, it's going to respond by making more CO. And if it makes more CO, that's less products, not more products. Adding NO2 to the system. So if I add NO2, it's going to use up that NO2 to make more stuff, and that's more product. What if I add CO2? If I add CO2, these two are going to hit each other more often, speeding up the reverse, and it's going to go that way, so that would make less products. So the answer was adding NO2 to the system. Okay. Okay. So this negative sign on the heat means that negative sign means it's a product. Okay. Combination of temperature and pressure. So pressure first. There's 3 moles of gas. There's only 2 moles of gas here, so more pressure would favor the side with the least gas, which is the right. So more pressure, so it's got to be a high pressure system, so I can cross off the low pressures. Okay, heat is a product. If I raise the temperature, it's going to use that heat to make the reactants. So I don't want to raise the temperature. If I lower the temperature, it's going to make more heat. So I'd want to do this at high pressure and low